I'm Anil Kumar. Welcome to my YouTube channel and the website globalmathinstitute.com. In this video, we'll discuss about complex numbers and how they can be represented geometrically. We'll talk about complex plane or Argand diagrams. On this, we're going to represent many complex numbers, their conjugates, and their multiples with I. We'll interpret the observations of these. We'll also represent the powers of complex numbers, interpret them. We'll see how vectors can be represented, and then we'll have few test questions. Just as Cartesian plane, a complex plane has two coordinates as shown here. A complex number, let's take an example, normally will be written as z equals to a plus bi. Now here, as you know, a is the real part, right? So this is the real part, and that is the imaginary part of this complex number, right? So on a Cartesian plane, as shown here, we are going to represent the real and the imaginary parts along horizontal and vertical axis. So the real part will be shown along the horizontal x-axis, and the imaginary part will be represented along the vertical axis, the center being at 0. Now let us take an example where, let's say, the complex number is just a real part. Let's say if we have z equals to, let's say 2. Now z equals to 2 really means a point which is along the x-axis, and that should be z equals to 2. If there is a point which is, let us say, z equals to minus 3, then minus 3 will be represented on the other side, and that becomes z equals to minus 3. So as you can see that the real parts are represented on the horizontal axis. On the other hand, if I have a pure imaginary number, and let's say we have z equals to 3i. Now I multiplied by 3, each unit is 1i, right? So 1, 2, 3. So this position here represent 3i. Correct? Let's take another unit here, another point. So let's say we take a point which is z equals to minus 4i. So minus 4i will be represented 1, 2, 3, 4, and that becomes minus 4i. Is that clear to you? So that is how we can represent pure, real, and imaginary parts. Now let's look into the complex number which has both imaginary and the real parts. So let's say we'll not name this as z1. So if z1 is, let us say, 2 plus 3i, then to represent 2 plus 3i, we can actually look into a position which is 2 units to the right, which is 1, 2, and 3 units up, that means 1, 2, 3. So this position here will represent the complex number 2 plus 3i, right? So this number here will be 2 plus 3i. Correct? Let me label these now. So this is 2 for us, that is 1, 2, 3i. Correct? Here we have minus 3. This is minus 4, and that is 0. Perfect. Now likewise, we could represent any number of complex numbers on this plane. So if I have another complex number z2 as, let us say, minus 2 plus I, that really means that minus 2 will be on this side and I right there. So this point here will represent the complex number minus 2 plus I. Is that clear to you? The complex number, which has both real and negative, real and imaginary parts as negative, will be represented in, which you can say, quadrant 3, right? Let's say if I have minus 3 minus 3i. So that means minus 3 and minus 3i will be a point here. Right? So that becomes your point Z3. Is that clear to you? Okay. So these are the ways in which you can represent a complex number on a plane. And this plane is called a complex plane. And the diagram shown is called Argand diagram. Correct? So we call this plane as a complex plane. And representing these complex numbers, we also call this as an Argand diagram. Let's move forward and see some interesting cases now. Now we are going to represent, we'll take up a complex number z and see what really happens when we take its negative or when we have its conjugate. So let's take one example. Let's say the complex number is z equals to, let's say 2 plus 3i. So let me first mark the point 2 plus 3i, which is 2 units to the right and 3 units up, right? So that becomes the position of 2 plus 3i. And that's our complex plane, correct? So this is our complex plane. In which this is the imaginary axis and here we have the real axis. Is it okay? And that becomes O, the origin. Now if I have minus z, then minus z will actually be minus 2 minus 3i. Correct? So minus 2 minus 3i means we'll go 2 units to the left and 3 units down. So what do you notice here? It is rotation by 180 degrees, right? So this, you can interpret this as a rotation by 180 degrees. You can say that, correct? Or you can say reflection about origin. Or you can also say it is reflection about origin. So in this way, you can interpret the complex number with its negative, right? Now let's talk about the conjugate. The conjugate of our complex number is 2 minus 3i, correct? 2 minus 3i means 2 and minus 3i means it will be positioned here. So that's the point which we are talking about. Now this means it is reflected on the real axis, right? So the conjugate is basically a reflection on real axis, the horizontal real axis. Is that clear to you? Right. So that is how you can interpret the conjugate when represented on a complex plane. Now let us see how to represent the negative of our conjugate. So that means we are now talking about the complex number minus 2 plus 3i. Now minus 2 plus 3i will be minus 2 plus 3i will be positioned at this point. Now that is a reflection of the previous one about the origin as expected, right? But if you compare with the original, then it is reflection on the imaginary axis, correct? So that is reflection of the complex number on imaginary axis. Is that clear, right? So if you compare with the original, which is z for us, in that case, minus z conjugate is a reflection on the imaginary axis, correct? So let me write the numbers as we move along. So we have minus z here, right? And that is the conjugate of our complex number. Now let's look into the position of iz. Iz will be 2i, and you multiply by I square will be negative, so get minus 3. So basically, Iz is minus 3, 2i. So minus 3, 2i will be where? So we have 1, 2, 3, and then 2i means going up, right? So that becomes the position of minus 3, 2i. Now if you compare this position with the original, then it is rotation by 90 degrees, right? So this is rotation by 90 degrees. Correct? So this is I times z. So if you compare with the original position, which is right here, right? And now, if I look into I times z, which is here, we see that this is a rotation clockwise, counterclockwise. So we can write down counterclockwise rotation by 90 degrees. So whenever you multiply by I, we do see a counterclockwise rotation by 90 degrees as shown in this particular diagram. Perfect. Now let's see what is the position of minus iz. Minus iz will be minus 2i plus 3. And the position here will be minus 2i, which is minus 2i, and plus 3 means 1, 2, 3. So that is going to be the position. Let me mark this as minus iz. So as compared to the original position, it is clockwise rotation by 90 degrees, right? Perfect. So we are comparing with the original position, all these. The next one here is iz conjugate. So the conjugate was 2 minus 3i. If I multiply this by I, we get 2i plus 3i, right? So if I'm going to multiply this by I and I becomes minus 1, so we get plus 3. So 2i plus 3, the position will be, let's mark this position now as 2i plus 3. So 3 on the real axis and 2 here. Right? So that becomes, so you basically see that as compared to the original, it is swapping of x and y coordinates. Right? So when you multiply, so as compared to the original, it is swapping of x and y coordinates, right? The last one here is iz conjugate. This is also equal to negative of iz conjugate. You can figure this out and check, right? So which is equal to, we are doing conjugate of iz now. So iz is 2i minus 3. And its conjugate will be minus 3 minus 2i, correct? So minus 3 minus 2i will be minus 3 and minus 2i. So that will be the position of iz conjugate. Is that clear to you? This was IZ, right? Conjugate, correct? So it is a reflection of IZ coordinate. So in this diagram, you can clearly see what really happens when we multiply the complex number by a negative number, by iota, the real, pure, imaginary part, and what happens when we consider their conjugates. So all the combinations, 6 of them, are shown here, and I hope you understand how they will be represented geometrically on a complex plane. Here is a very interesting example. We need to represent a complex number z to the power of n, where n is equals to -1, 0, 1, and 2. And then we have to interpret the observations as we represent the powers of a complex number. So what we have is a complex plane here. We also call this as Argand diagram. Now, on complex plane, we have a real axis and an imaginary axis. The center will be treated as 0, as we see in Cartesian plane. So if you compare with the Cartesian plane, the horizontal axis is the real axis and the vertical axis is representing the imaginary numbers. We'll take an example. Let's say z. Let's take a pure imaginary number first, and then we look into its powers, right? Let's say z is equals to, let it be 2i. Okay. So we are taking a pure imaginary number, z equals to 2i. And then we'll see how to represent these powers. So z to the power of -1 basically means 2i to the power of -1, right? And that is, we have 1 over 2i, correct? Now we can multiply and divide by I. So if I do that, we get I over -2, right? So what we did was, we multiplied and divide by I, which is negative of half I. Correct? So z to the power of -1 can be represented by a point which is minus half of I. So this is 1 unit, so minus half of I will be the point right there. Is that clear to you? Correct? So that becomes the first point, which is minus half of I. Now let's talk about z to the power of 0, which means 2i to the power of 0. Anything to the power of 0 is just 1, and let me represent this by green color. So that will be a real value of 1. Is that clear to you? Now, let's talk about power as 1. So z to the power of 1 will be 2i, right? So 2i, whose magnitude now is 2, right? And this will be represented on the imaginary axis right there. Clear? So you can see that if you join it with the origin, we are actually moving by 90 degrees counterclockwise. Now let's take z square. That means 2i whole square, and that means 4i square, or negative 4. So this number, negative 4, will be represented 1, 2, 3, 4 on this side. 1, 2, 3, 4 right there. Is that clear to you? So that is the next position for us. So what do you observe? Observation here is that multiplication by I, we can write down here, by I. That is one thing which we are doing as we multiply, right? Results into what? It is 90 degrees counterclockwise rotation. That is one thing. Another thing which you notice here is the magnitude is, of course, it is power of n. So every time you're multiplying by the magnitude 2. So in this case, the second observation is that the magnitude is times 2 each time, right? It's half times 2 times 2 and times 2. So the magnitude is magnitude of the original to the power of n, correct? So that is expected. Perfect. So in our case, we are multiplying by 2 each time, right? Which is times 2. Since the magnitude of this complex number is 2. Perfect. And therefore, we did observe that two things happen, and that is one, there is a rotation clockwise, counterclockwise by 90 degrees, and second is that the magnitude power is to be considered. Perfect. Now, keeping this in view, we can now take some complex numbers, right? General complex numbers, and then see what really happens. So this time, let me take a complex number z. We'll keep it simple. Let's say 1 minus I, right? Let this be our complex number. In that case, z to the power of minus 1 will be 1 over 1 minus I. Now, to find real and imaginary parts, we could multiply and divide by its conjugate, which is, I should write 1 plus I. So we'll multiply and divide by 1 plus I. So what we get here is 1 plus I over a square plus b square, right? So it is 1 plus 1, which is 2. So that is equal to half plus half I. Is that clear to you? Okay. So half plus half I, z to the power of minus 1, can be represented as a point which is half plus half I right there. Correct? So that is how we are going to represent the very first point, which is z to the power of minus 1. Now, what is z? Z is given to us as 1 minus I. So 1 minus I can be represented as 1 and then minus I, right? So that becomes 1 minus I, correct? In between, we forgot to the power of 0, right? So let me also write down here z to the power of 0, which is actually 1, correct? So let me write down 1, which is right there. The point. Now, the next point which we are going to consider is z to the power of 2 square, right? Or 1 minus I whole square. And that is 1 minus 2I plus I square, or we could write this as 1 minus 2I minus 1, and this is actually equals to minus 2I. So minus 2I will be a point on, so minus 2I will be this point. So what do you notice, right? We can actually continue this process. So what do you notice? So as we observed earlier, our observation is kind of like this. So basically there are two observations. One is, in this particular case, since it is 1 minus I, we have a clockwise rotation 90 degrees, clockwise rotation, right? And second, the magnitude of z is basically 1 plus 1, right? So square root of 1 plus 1. So which is equal to, as we are seeing, the magnitude of z is basically equals to a square plus b square square root, right? Which is square root 2. Let's write down. So magnitude is 1 square plus 1 square, which is equals to square root of 2. So what we observe here is that the powers are square root 2 to the power of n as we move along this particular path, right? So we'll have a path as shown here. Each time, if you join from the origin, then the length from the origin will be square root 2 times the previous position, right? And it will be rotated by an angle, which is 45 degrees, not 90 degrees. So in this case, it is clockwise rotation by 45 degrees, right? This is half, right? This is right in the center. So it is a clockwise rotation by 45 degrees. Yes, that makes sense. So if you have the complex number z, whose magnitude is square root 2, correct? And 1 minus I, in that case, the powers of n, we have a rotation by 45 degrees clockwise. And each time the distance from the origin will be square root times 2 the previous number. Does make sense to you? So that is the kind of observation of which you will see when you are representing z to the power of n. I hope that makes sense. Now we'll actually talk about this more on polar coordinates, right? So since we are talking about rotation, it will be check video on polar coordinates for angle calculations. That will be better actually. So at present, when we're talking about the complex plane, we can kind of estimate this to 45 degrees in this particular case. But in general, we can accurately find the rotational angles using polar coordinates. So that will take up in another part of the video. I hope that makes sense. So I hope you understood how the powers of a complex number can be represented on a geometrically on a complex plane. Discuss how to represent complex numbers as position vectors. So we have been talking about complex numbers z being represented as a plus bi. Now we can also write the same complex number in column form a and b, right? So this form helps us to perform operations, especially addition and subtraction, very simple and is used many times. So we are going to actually use this nomenclature and then show how to add and subtract complex numbers. So we'll also refer to two different ways of representing the complex number, where one is, we'll say, a position vector. So if I represent a vector whose A is the value along the real axis and B is the value along the imaginary axis, so in this case A and B, this vector could be AB if this value is A here and that is BI. So a directed vector with tail at the origin, so that's the origin. So what we are saying here is a directed vector. You can say directed segment with tail at the origin. Right, a tail at the origin. And length of segment equal to magnitude of vector. Normally magnitude will be the absolute value written like this. In this case the magnitude will be a square plus b square square root. Correct? So that is the directed vector and we call this as the position vector. Perfect. So we are going to represent our complex numbers as position vectors shown here, and then we'll also see how to add and subtract vectors. So to add and subtract, we'll have two different ways of doing it. So if I have a vector, let's say this is one vector and the other vector is kind of like this, in that case we could add these vectors by forming a parallelogram. Right, so in that case the vector which is the diagonal of this parallelogram is sum of these two vectors. So if I have vector u and a vector v, then this vector is u plus v. To find the difference, we could actually have the other diagonal. So if I sketch the other diagonal, which is, let us say this, then this vector will be u minus v. Is that clear to you? So that method is parallelogram, right? So that is parallelogram. And we also have a triangle. So in triangle, you actually place the tail of the other vector on the head of the first one. So if this is my u, then the vector v, which will be translated so that its tail is on this, and the sum of these two vectors will be shown by the third side of the triangle. So that becomes u plus v, right? If this is your vector u and the other vector is v. So we'll now in details understand what we just talked about. So we'll talk about complex numbers in different forms, and then we'll show how to represent the complex numbers as a position vector. So let me write few complex numbers here. Let's say z equals to 2 plus 3i, right? So that is a complex number. This number can be represented on this complex plane also. This is referred to as Argand diagram. Where this horizontal axis is the real axis and the vertical is the imaginary axis, origin being at their intersection. The complex number z, 2 plus 3i, will be represented with 2 along the real side, 3i, and so that number is basically the complex number 2 plus 3i. Now, you can also represent this as a vector. So let me say the vector z could also be written as, we can write this as 2, 3. Now, we are writing this as a vector in column form, and we are going to represent this as a position vector on the complex plane. So we'll write this as a position vector. So when I say position vector, it really means that the tail is at the origin, right? So we say tail at the origin, right? So if the tail is at the origin, and now we need to sketch this position vector, then be represented by a segment with direction, right? So this directed segment, we can call this as O to P, for example. So we say OP is representing the position vector 2, 3. So it is a directed segment, as you can see on this complex plane. So that is a way to represent complex numbers as position vectors. So when we say complex number, so remember, when we say number, it means a point, correct? And this point is this point P. And when we say position vector, it means this segment, directed segment, right, with the arrowhead. So vectors have magnitude and direction. So the magnitude of this vector OP is given by the length, and this is equal to, in this case, square root of 2 square plus 3 square, which will be square root of 4 plus 9, or square root of 13. So this length will be square root of 13, which represents the directed vector OP. So I hope that makes sense, right? Now you could represent any vector written in many different forms on a complex plane. Now let's write down few vectors and represent them on the complex plane. So we could have a vector z equals to minus 3i. So if I write z equals to minus 3i plus, let's say, 2j, where I and j now are the unit vectors. So in this case, when I write like this, so this complex number, in this case, I and j are unit vectors. So that complex number can also be represented here as minus 3i means 1, 2, 3, and 2j means this. So in that case, when you are representing unit vectors I and j, then basically this becomes vector j and that becomes vector I. So I've kind of mixed this up. However, when we are talking about the complex numbers, we'll prefer to write this as minus 3, 2. So that is your complex number. Now when we say represent this as a position vector, in that case we kind of draw what we had shown here. So -3, so -3 on the real axis and 2 on the imaginary axis gives you this arrowhead, which represents that vector. So in this part of the video, we have learned how to represent complex numbers as position vectors. So remember, position vectors will have a tail at the origin and a directed segment. Length of the segment is proportional to the magnitude of the complex number. Perfect? Now, let us also see how to add and subtract complex numbers when they are represented as position vectors. Now, let us take an example to illustrate how to represent sum of complex numbers. We are considering position vectors. Okay, so let's say we have a vector u, which is, let's say, 2 plus 3i. We'll normally write this vector as u as 2, 3. So, and we can sketch this vector 2 and 1, 2, 3. So this vector from the origin represents the position vector u. So that's the origin for us. This is real axis and that is the imaginary axis. Let's take another vector v, which can be, let us say, let's say 4 minus 5, which we will write this as 4 minus 5. And then we'll try to add these two vectors, u and v. The result will be 2 minus 4 and 3 minus. Add means plus, right? 2 and 4. Add the corresponding x values and the y values. 3 minus 5. And the result will be 6, and that is minus 2, right? Let us see on the complex plane how this is performed. So now, the vector v, which is 4 minus 5, will be 1, 2, 3, 4. 1, 2, 3, 4, 5, right? So this vector, the position vector will be from the origin to this point, right? Now to get the resultant, we try to complete the parallelogram. So the step here is to complete parallelogram, then diagonal from origin represents sum u plus v. Is that clear to you, right? So let's do this. So drawing a line parallel, which is from here, 4 minus 5, we can go from here 1, 2, 3, 4, 1, 2, 3, 4, 5, right? So that should be connected to form a parallelogram, correct? So we know the opposite sides are now parallel in the diagonal. From the origin of this parallelogram represents the sum u plus v. Is that clear to you? You can clearly see that the result here is 6 minus 2, as expected. Perfect. So that is how you actually add the complex numbers using vectors We'll again do the same thing, but this time we'll use a triangle to perform the addition. So now let us see how to add vectors using triangle. Now both methods are commonly used. So the idea here is, let's take some example. Let's say u is equal to, let's take a vector which is, let's say 2 minus 3. So this vector u is 2 minus 3. Let me sketch this. 2 minus 3 means here, right? So this is the vector 2 minus 3 for us, the vector u. We want to add to this the vector v, which is, let us say, equals to, let's say we have 3, 5. So now, if you want to make a triangle and use triangle to perform the addition, then the vector v is placed with tail at the head of the u, right? So place tail of vector v on the head of u. Perfect. And then we have a vector 3, 5. So from this position, we go 3 units right, which is the real part, 1, 2, 3, and 5 up. So 3 and 2, 5. So that's the vector v. Correct? Now the resultant, u plus v, is right there. So u plus v will be the vector shown here. So that vector will be u plus v. Is that clear to you? This is from the origin O. This is our real axis, and that's the imaginary axis of our complex plane. You can also see that u plus v will be 2 minus 3 plus 3, 5, which is 2 plus 3 is 5, and this is 2. So you can note here 1, 2, 3, 4, 5, 2, right? So this vector is indeed 5, 2. Is that clear to you? So that is how you can perform addition of complex numbers when you are using the vector method, right? So using a triangle, that's how we can actually add them. Now let us see how to subtract the complex numbers, again using position vectors. Let's take an example here as u equals to, let's say 3, 4. Let me write like this only. And v equals to, let me sketch. So u is 3, 4 for us. So we have 1, 2, 3, and 4. 1, 2, 3, 4, right? So that becomes the vector u. Three, 4. Now we want to subtract the vector v. So let's take this vector as minus 2. Let's say minus 2 minus 3. Okay. So I'm going with the space which I have. So vector v is minus 2 minus 3, which will be represented as minus 2 and minus 3. So that is vector v for us, correct? So we have vector u and vector v. Now if I have to perform the operation u minus v, these are vectors, then the result will be, as you can see, 3 minus of minus 2, 4 minus of minus 3, and what you get here is 5, and that is 3 plus 4 as 7. So that should be the result. Now, how do we do it geometrically? So basically, what we are going to do here is we are going to add, when I say u minus v, it is same as adding negative of v to vector u. So let me sketch negative of v here. Means rotation by 180 degrees, right? So instead of minus 2 minus 3, now it will be 2, 3. So that is negative of v. So adding these two, we get our result. Now the addition can be performed by completing the parallelogram. Perfect. So let's make a parallelogram now. So from this point, we will go 3, 4. Sorry, this was 3 minus 4, right? We went down 4 steps. So this is minus 4. So minus 4 plus 3 is minus 1, sorry. So this should be 5 minus 1. So I've sketched it downwards. That means it should have been minus 4, okay? Right. So now let's complete this. So from this point, we'll go 3 minus 4. So 1, 2, 3, 1, 2, 3, 4. And that will be a vector parallel to the vector u. Perfect. As you can see, we can now complete our parallelogram, and the diagonal of this parallelogram is the difference of the two vectors, right? So this is u minus v. Is that clear to you? Correct? So treat minus as addition of the negative vector. So that ways you could use what you learned earlier, how to add vectors even to subtract vectors. So I hope that makes sense, right? So this is the origin, that is your real axis, and that's the imaginary axis. Perfect. So that is how you would actually subtract the two vectors. So with this, we come to an end of learning how to add and subtract complex numbers using position vectors. Perfect. I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.